Good morning to everyone, distinguished chief guest, respected Nobel Laureate Professor Moungi G. Bawendi. Unfortunately, our Chancellor is unable to attend. As you heard before, there was an urgent inspection by the Government of India in one of our other units, so he had to be away on that assignment. He conveys his greetings and his wishes to all of you and to the august gathering today. Respected Vice Chancellor Dr. Vikas Mishra, esteemed dignitaries on the dais, off the dais, renowned scientists, academicians, industry leaders, and innovators. Dear faculty members, researchers, students, and delegates from India and abroad, members of the press, ladies and gentlemen, it is indeed a great day at Hindustan Group of Institutions today. Yet again, we have a very important guest and our friends from across the planet. It is with pride and profound pleasure that I address this gathering on the occasion of the International Conference on Quantum Horizons 2025. I extend my warmest greetings and a heartfelt welcome to all of you. At the outset, I would like to express our deep sense of honor in hosting the Nobel Laureate Professor Bawendi as a chief guest for this conference. Your presence amongst us is not only a celebration of scientific excellence, but also a powerful inspiration for our students and young researchers who aspire to push the boundaries of knowledge and innovation. I also welcome our distinguished keynote speakers, panelists, advisors, industry leaders, and collaborators who have joined us from across the globe. The theme of this conference, as mentioned by the Vice Chancellor, captures the defining challenges and opportunities of our times. Last night we had a very beautiful dinner for our guests from overseas, and we had quite an inspiring discussion about where we are heading as youngsters, where you all need to be heading, and the concerns which we all talk about today, the environment. Sometimes when you're with such leaders who does so much for society, it is so important and relevant because it churns the best in you for the benefit of mankind. So I think last night was a wonderful dinner. Some of you were part of the dinner last night, and perhaps someday you will also share a chair with such experts, hopefully. From quantum computing and secure communications to advanced materials, clean energy, artificial intelligence, and sustainable manufacturing, these technologies are redefining how societies function, economies grow, and nations compete. As educators and institutional leaders, we must ask ourselves a fundamental question. How do we prepare our students and research ecosystems for a future driven by such transformative science? At our group of institutions, our answer has always been clear: by fostering excellence in education, relevance in research, and responsibility towards society. At HITS and our group of institutions, we're completing almost 4 decades at our university and almost 6 decades our group of institution. Our founder started it way back in '66. We'll be celebrating yet another milestone very soon. We have consistently evolved to meet the changing demands of science, technology, and industry. Our collaborations with KCG College of Technology for this conference reflects our belief that institutional partnerships strengthen innovation ecosystems. Together, we aim to create platforms where ideas flow freely across disciplines, institutions, and national boundaries. The conference has been thoughtfully designed to encourage cross-pollination of ideas. The inaugural session has many lectures, panel discussions on quantum materials and intelligent technologies. The interactions and technical sessions bring together physicists, chemists, natural material scientists, computer scientists, engineers, and industry practitioners. This convergence is essential because today's breakthroughs rarely occur in isolation. They emerge as the intersection of disciplines. Equally important is the role of industry and innovation hubs represented here today. Intelligent technologies must move beyond labs into scalable, affordable, and sustainable solutions. Industry-academia collaboration is no longer optional, it is essential for national progress. Platforms like Quantum Horizons help align research priorities with societal needs, industrial capabilities, and global sustainability goals. Sustainability, in fact, must remain at the heart of all technological advancement. As we pursue quantum and intelligent technologies, we must ensure that they contribute to clean energy transitions, resource efficiency, climate resilience, and inclusive growth. From an institutional perspective, we view conferences like this not merely as academic events, but as strategic investments in the future. They help build global networks, attract talent, inspire innovation, and reinforce India's position in advanced science and technology. I firmly believe that India has intellectual capacity, youthful energy, and entrepreneurial spirit to emerge as a global leader in quantum and intelligent technologies, provided we continue to invest in education, research, infrastructure, and international collaborations. I would like to take this opportunity to acknowledge the tireless efforts of the conference chair, organizing committee conveners, coordinators, faculty members, and the volunteers across the faculty members and the students from both the institutions who are organizing the event. The dedication and teamwork have made this prestigious conference a reality. I also thank our sponsors, advisory committee members, and international partners for their valuable support. As we commence this conference, I urge all participants to engage openly, question boldly, collaborate generously, and think beyond conventional boundaries. Let the discussions over the next 2 days plant the seeds of new ideas, partnerships, and innovations that extend far beyond this auditorium. In conclusion, I am confident that Quantum Horizons 25 will not only enrich our scientific understanding, but also strengthen our collective commitment to building a knowledge-driven, technologically advanced, and sustainable future. I would also like to mention my recognized Dr. Ajayan, who was kind enough to invite me and our academic, some of our researchers, to his wonderful University of Newcastle in Sydney last year for the 5th International Conference on Emerging Advanced Nanomaterials at Newcastle, University of Newcastle. Wonderful event attended by Nobel Laureates. That's where I met Professor Bawendi, and his talk on nanomaterials was excellent. The conference lasted for 5 days, morning to evening sessions. It was very technical, so I could only spend 1 day, beyond which would not be possible for me to understand. However, the lectures were wonderful. There were professors from all over the world. And the wonderful point I'd like to mention, as a leading researcher in nanomaterials, he has one of the best centers in Australia. I hope some of you, he has given wonderful opportunities for our staff and students to get trained there. If you do get an opportunity, please make sure you don't miss it. He's a great professor and a leader. I think all of you must look upon to him and appreciate his quality of knowing each and everyone's name in that wonderful conference. He would call them all out, each of the speakers by name and designation, and that's how much he values the social capital which he has developed over the years. And that's what brings the best research resources to him anytime, all the time. And I must thank him for bringing a wonderful guest to our campus today, so all of us may experience and learn from him, and of course Dr. Ajayan and all the other delegates who have come from across India and other countries. So I wish you all the best once again, and thank you all for being a part of this wonderful event. And I look forward to also the panel discussion which will follow this. We have a lot of children from across many schools who have eagerly signed up, and they have some questions they would like to ask the panel. I hope the panel will be able to satisfy the scientific thirst and hunger of our youngsters of our country. Thank you.
Respected Chancellor, Dr. Anand Jacob Verghese, Pro-Chancellor, Dr. Ashok George Verghese, Executive Director, Dr. Ebi Sam, Vice Chancellor, Dr. Vikas Mishra, distinguished dignitaries on the dais, esteemed speakers, faculty members, researchers, and my dear students. A very good morning to everyone present here today. I would like to also share that our Chancellor, Dr. Anand Jacob Verghese, though unable to join us this morning due to prior commitments, sends his warm greetings and best wishes for the success of Quantum Horizons 2025 and to everyone gathered here today. It is a rare privilege in the life of any institution to welcome someone whose work has not only shaped a field of science, but has reshaped how humanity understands the invisible world around us. Today is one such moment. I have the honor of introducing our chief guest, Nobel Laureate Dr. Moungi G. Bawendi, Professor of Chemistry at the Massachusetts Institute of Technology. Dr. Bawendi did not simply study quantum dots. He redefined them. At a time when the field was unpredictable, unstable, and scientifically daunting, he chose not to step back. Instead, through clarity, patience, and visionary thinking, he transformed quantum dots from scientific curiosities into one of the most impactful materials of our era, now used in advanced displays, medical diagnostics, bioimaging, and emerging clean energy technologies. After receiving the Nobel Prize, Dr. Bawendi shared a profound thought. Great science happens when people feel free, free to think, free to fail, and free to explore. That philosophy resonates deeply with the spirit we want to cultivate here at Hindustan, a culture where curiosity is encouraged, where experimentation is celebrated, and where young minds dare to challenge the status quo. Across 3 decades at MIT, Dr. Bawendi has nurtured hundreds of scientists, not merely to achieve academic excellence, but to become innovators who positively shape society. Many of his mentees now lead influential research laboratories, build pioneering companies, and push the frontiers of sustainability, medicine, and technology. As we gather here to explore quantum horizons, new materials, intelligent technologies, and sustainable futures, Dr. Bawendi stands as a powerful reminder that the future is built by those who push beyond what is known and imagine what is possible. Ladies and gentlemen, it is with immense respect and pride that I welcome our chief guest, Nobel Laureate Dr. Moungi G. Bawendi.
Unique properties of this nanomaterial and lead in new technologies, and that can change the life of so many people, from display technologies to drug delivery system to even sensing technology, covering energy, environment, and health. Today in my talk, I am going to show you some of the materials and how we can change the properties of the material by simply changing the nature of the elements and structure, morphology, and even porosity of this material. For example, carbon. With the nanoporous structures, and it may be a partially conducting, but depending on the framework, it may be a conducting material. But if you change the framework from carbon to carbon nitride, it will become semiconducting material. But if it is a boron nitride, and it will become insulating material. So by changing the nature of the elements in the framework structure of the material, one can change the properties of this material. But not only that, it can change the surface, catalytic, and sensing properties of the material, and that can dictate the performance of the material in various applications that is shown here. For example, carbon capture and conversion, clean energy generation, energy storage and conversion, and even the drug delivery system. And over the last 25 years, my team discovered a series of advanced nanostructures, including a nanoporous carbon nitride, nanoporous boron nitride, nanoporous boron carbon nitride, nanoporous fullerene, nanoporous biomolecule, and even various carbon-based nanostructures, and published quite a lot of papers in top quality journals. Also, we use a theoretical calculation to understand and predict the performance of the material. or to know more about this material. And once you know that, and we can apply them for various applications including energy storage, carbon capture and conversion, and even the drug delivery. But these are all the fascinating material that you can see here. See, they have got a highly ordered structures and then unique morphology with a fascinating conducting, semiconducting and insulating characteristics. But preparing the material is not only enough, but he has beautifully demonstrated that how these materials can be available to make an impact to the world and to the society. That is the key. That is the key for the success, and that got him the Nobel Prize. And today I am going to show you the material that I have discovered in our lab have the potential to change the world or to save the world or to help the society. And how? I'm going to take you in a few minutes that the world is facing. And what are the problems that we are facing? So one of the problems is this global warming. And from where it is coming from? The CO2 concentration in the atmosphere. 400,000 years ago, 400,000 years ago, the CO2 level in the atmosphere is less than 250 ppm. It was going up and down till 1950. And after 1950, you see there is a huge rise in the CO2 emission. See, 400,000 years in the nature, Dr. Ashok was telling that nature has its own mechanism. Yes, of course. And it was just managing it till 1950. But after 1950, after the automatic revolution, right? We have been so greedy that we continue to use large quantity of the gasoline or coal kinds of energy that liberated huge quantity of the CO2 to the atmosphere. But in the current level is a 430 ppm, which is an alarming level. And why we are worried about the CO2? The CO2 is a nasty molecule that has a tendency to absorb the heat that is reflecting back from the earth. And once it absorbs the heat, that heat will be reflecting back to the earth and warming up the earth. And you see the rise of the temperature all over the world. Drought everywhere, killing hundreds of thousands of people. Right? And from where it is generated? The fossil fuels, coals, oil, and so on. We have 8 billion people and we need 580 exajoules of energy. All energy is coming, most of the energy is coming from the fossil fuels, and that emits huge quantity of the CO2. And if you don't take it seriously, and this is going to be a disaster, because the population is going to be exploded, and it is going to be 10 billion or 11 billion in 2100. Everybody needs energy, but in 2050 we need 750 exajoules of energy. And 2025 alone, we liberated more than 36 billion ton of CO2 to the atmosphere. And if it goes like that, it will be 40 billion tons of CO2. That is a huge. Of course, nature has its own mechanism. That ocean, which is a basic in nature, CO2 is acidic in nature. It can take 70 to 80% of the CO2. And people can say that, yes, it is huge. It can even take more. But ladies and gentlemen, the issue is, when the ocean takes too much of CO2, it gets acidified. When it gets acidified, it affects the living organisms in the ocean. That's a huge issue. So the global warming and affecting the living organisms in the ocean. Right? So that's why now the researchers and politicians are jumping into finding a solution. Okay, Can we increase the efficiency of the energy to solve the problem? Or develop a renewable energy expansion? Or use some innovative strategy to find a new form of energy technology that Professor Bawendi was mentioning? It's not only single technology, but there are so many low energy technology that people can use it. Or public awareness or the policy development. Because this is quite crucial. Because we have to tell our kids, when you go out of the house, you turn off the light. And if you wanted to walk 1 kilometer, right? So you walk, don't take the car, right? Unnecessarily you are just, damaging the air. But that takes a lot of time. But it should come from the education. It may take 20 to 30 years, but we don't know whether the world will survive or not if the situation continues like that. So that is one of the reasons why people are jumping into a clean energy technologies, and one of that type is a hydrogen. Why hydrogen? When it burns, it won't emit any CO2. It has got a high energy density. It can be stored without losing its energy. And you have a huge quantity of the resources, the seawater, that you can convert, if you have the technology, convert it into the hydrogen. But it has got a lot of unique properties and opportunities. But the current technology to produce the hydrogen is mainly coming from this natural gas, crude oil or the coal. To produce 1 kg of hydrogen, people are generating 10 kg of CO2. But to meet our demand, it's almost 94 million tons of hydrogen that we need now. But in 2050, we need 530 million tons of hydrogen. If you use the existing technology, you can simply calculate 5,300 tons of CO2 will be liberated to the atmosphere. So what are the current technologies? The green hydrogen production, which is mainly coming from the natural gas, right? But it's a crude technology, but it emits a lot of CO2, right? And the cost is less, but you can't just use it because it's detrimental to the atmosphere or the air. Then people are jumping into green hydrogen production. That's the electrolysis of water. So use electricity to split water into hydrogen and oxygen. But the issue is you need high purity water and also highly expensive noble metal catalyst, but the cost of producing hydrogen is quite high. That's a major problem. Then people are jumping into photocatalytic production of hydrogen, that you can use the sunlight. But with the new photocatalyst. But the issue here is that with the current photocatalyst gives less than 1% solar to hydrogen conversion efficiency, which is not enough for the commercial production of the hydrogen with a lower cost. Even though we have huge quantity of the sun energy, but the efficiency of that material that is currently available is very poor. So we have the sun energy hitting the earth is 885 million terawatt hour. We have enough energy, free energy that is available. But when they talk about hydrogen, they are not thinking about the source of water. This is a critical thing. Because to split the water through electrolysis, you need a high purity water. Right? But how much water we have in this world? So we have 333 million cubic miles of water. In that, 97% is a seawater. And only 0.3% is in the form of river, lake, or the glaciers or whatever. Even with that water, Tamil Nadu is fighting with Kerala, Kerala is fighting with Karnataka, and Kerala is fighting with maybe Andhra Pradesh. Every state is fighting because we don't have a water. If we start to use that river water or lake water for the electrolysis, and you are going to create another social problem. Because you need a high purity water. Because to produce 1 kg of hydrogen, you need 10 kg of water. But how much electricity that you need? To make 1 kg of hydrogen, you need 55 kilowatt hour energy. To convert 1000 liters of water, right? For example, so if you convert the sea water into normal water through the desalination process, you need 3.3 times more water anyway. And you need 5500 kilowatt hour energy. That's a lot. Just to convert 1000 liters of water. To overcome all these drawbacks, and our center has been developing a new form of the catalyst so that can use the sun energy and split the seawater into hydrogen. And this is a technology, that's a groundbreaking technology that I am going to present to you. But just producing hydrogen is only enough? No. Once you produce hydrogen, what you are going to do with that hydrogen? You have to generate energy. But to generate energy, you need another technology. That's a fuel cell technology. But fuel cell generates electrical energy. But then to use that energy, right, continuously, you may have to store it somewhere. Then you need energy storage devices, right? So what we need is an integrated approach of harvesting that energy from the sun and generate that energy and store it. And when the sun is there, you can generate those energy. But when the sun is not there, the sun will be there for only 8 hours. But after that, then you can use the stored energy for, your purposes, the clean energy. And also, you need to also develop the technology to capture and convert that CO2 into a clean fuel using this material technology. So that is a device that we are developing at the University of Newcastle in my center, Global Innovative Center for Advanced Nanomaterial. So it is an integrated approach like fuel cell, photocatalysis, energy storage, and even the carbon capture and conversion. So if you can integrate everything, you can drive a car without gasoline or fuels, petroleum or the diesel, just with the sunlight and seawater. And what you need is this material. Right? Today in my talk, I'm going to show you how to make this fascinating material and how we can tune the electronic or electrical or semiconducting properties of the material to make it available for making this ultimate clean energy storage conversion device. So what is that material? It's a carbon nitride. So carbon nitride is the organic semiconducting material which has a band gap of 2.7 electron volt. There are 5 different kinds of carbon nitride: alpha, beta, graphitic, cubic and pseudo-cubic carbon nitride. But among this carbon nitride, the graphitic carbon nitride can be synthesized in a lab in a large quantity. But other carbon nitride, you need a very high pressure and temperatures to make it. You need a large quantity. You need a large quantity of the material if you wanted to make the device for the continuous production of energy. But with the high pressure technology, you can make only the few milligrams of the catalyst. That's not enough. That's not commercially viable. So that's why people are interested in this graphitic carbon nitride that has got a unique structure. The tris-triazine structure, but that can be synthesized by the chemical or molecular precursors at a high temperature. We normally use this melamine or a cyanamide or a urea or a thiourea. You heat it up to high temperature and then you take it out and check the performance of this material, and then you will get the semiconducting characteristics as 2.7. But the problem with this material is that it has got poor specific surface area. Even though it has got a poor surface area, many people try to use this one because of this unique semiconducting property. It's mainly in CO2 absorption because it's a basic in nature, and with the just moisture you can convert that into methanol or methane, and then you can even use that as photocatalyst for the degradation purpose or the hydrogen production. But the performance of the material is very poor because of the low crystallinity and low conductivity, and is a fast electron hole recombination. So the band gap is 2.7, and that gives them only the limited visible light harvesting. So to overcome these challenges, so our center tried different approaches to improve the properties of this carbon nitrate material by introducing the nanoporosity or changing the surface functional groups of this material to introduce the new property, or change the electronic conductivity of this material, or tune the band gap to introduce new characteristics, and then of course changing the wall structure from amorphous to crystalline, or even create the diffuses. By tuning or by adding these functionalities in your carbon nitrate material, you can create a series of the material with unique characteristics, and that will be useful for the splitting the sea water into hydrogen.